Hello everyone, my name is Gustavo, Gustavo Mota Freire. I'm from University of São Paulo, and I'm about to present you guys my first abstract article. The title of this paper is A Distributed Software Architecture Based on Reactive Microservices for the Smart Building Context. This paper was written through the ECMC USP, which is the Institute of Mathematics and Computer Science based on São Paulo, Brazil. So this is the agenda of this research. We're going to first give you an introduction, and then we had the second session about the objectives, then the third section about the proposal architecture, and at the end we're going to have the conclusions. So pretty much we have some context about the definitions of the areas that we are researching. So first we have this context about the smart building. So we have the source referencing that the global population will grow at such a high speed that at the end of 2050 the amount of energy required to run all these buildings and to run the whole civilization is going to double. And also we have this interesting fact that 90% of the time is going to be spent inside the buildings. So we are talking here of doubling the demands, and also a big concentration of this time we're going to spend at buildings. So we have here an excellent opportunity to improve the quality of the building's technology. Also, we have some context about distributed software architecture. So the goal of distributed software architecture are to improve scalability and allowing the system to expand and to include more device and sensor without compromising performance. So in order to scale this kind of architecture, we need to use the distributed systems as much as possible. All the philosophy and the implementation that the state of the art of distributed architectures are required to minimize latency, efficient response. So in order to have these smart systems, we need to have a distributed system supporting all of these new demands of different sensors and all of that. So the main objective here is that we want to implement distributed software architecture following the reactive manifesto, design and cloud patterns, cloud computing capable of supporting these complex and scalable demands of the systems. And to do that, we are going to work through synthetic data to validate our architecture, and also we're going to actually implement the architecture at the ECMS USP, at the lab at ECMS USP. But the idea here is to have an overall architecture that aims to different environments, not only the lab, also hospitals, also college campus, overall college campus, and these different environments that can benefit from this architecture. So here we can see the three main architectural layers, if you are considering the 3 layers architecture. So we have the application layer where it's the application they sit. We have the network layer, that you have the protocols, the clouds, and so on. And we have the third major layer, which is the perception layer. So the sensors, actuators, and so on. So this architecture is going to focus only on the first and second, or second and third level of the 3 layers architecture. So that's our main focus here: optimize the network, the cloud, and the application. So here we can see a conceptual view of this architecture. So at the left we have the inputs, so the sensor data, and at the right we have the consumer, so the client. So starting from the input, we have sensor data. These sensors are going to produce huge volume of data, and we're going to use the MQTT protocol to communicate this data. So this is the first node of our system, is a MQTT broker. So pretty much this broker, this node, the responsibility is translating the sensor information using MQTT protocol to a different protocol. In this case, we are using a message broker here. And this message broker is going to receive the information from the MQTT broker. So both brokers, they have the same goals of using publisher subscribers pattern. The idea here is to decouple the consumers from the producers, and also by using these we can have a sync message. So if we have also more resilience, which is something that also we want to have for the reactive. We have more responsiveness, reliability, because if we lose, we have some transitory problem, something like that, we still are persisting the information asynchronously. So we don't depend of the consumer to acknowledge that they are receiving the information. So that's the goal of these two brokers. So we have topics through these brokers, and we're going to receive information. So you can think about a topic for sensor of temperature, a topic for a sensor, I don't know, about vibrations and so on. So that's the goal. So these are the backbone of the system. And then we have the heartbeat and circuit breaking microservices. These microservices, the heartbeat is just to keep the broker alive. So from time to time we send some signals so the consumers don't time out. And the circuit breaker is also about that. It's also about testing, and also making sure that whenever we have too much retries, at some point we need to stop the retry. So that's the goal of the circuit breaker, having a way to do retries but also control, so we don't have like a waste of resource. And then we have the ingester. The ingester is so as you guys can see, this is ETL flow. So we have the extraction, which is the sensor, and the ingester is the transform of the ETL. The T and the ETL stand for transform. So we're going to consume the information from the broker, make transformation. So depending of the business requirements, we may change an object to a different object, or enhance a different object, have extra fields, or have some business logic. So all of these business transformations and data transformations, they work through the ingesters. The ingester is going to persist the information relational database, SQL, so it makes easy to create queries and all of that. And you can also note that we have a line that is connecting from the message broker to a NoSQL database. This is a CDC approach, so we have a way to log everything from the broker and then project that on a non-relational database, which is the NoSQL database. And this provides a different paradigm. So for example, for time series, this may be useful because it's already a time series database, or for example, a graph database, depending on the use case. So as you guys can see, this is a base architecture. Not necessarily going to use all the nodes. We may use, depending on the requirement, but most scenarios we're going to select the node that we want. So we also have the cache. The cache is responsible for retrieval of very frequent queries, so we don't overload the database. And then at the last layer we have the interface, the APIs that is going to expose this information. So we have an API for the NoSQL database, we have an API for the SQL, and an API for the cache. In this case, we are using the cache as a WebSocket API, so we have real-time information. In front of all these API layers, we have the API gateway that is responsible for helping with the security. We are not clearly separate the security from the API gateway, but that's the goal of the API gateway, and have and being as an entry point of the architecture. So we can, again, the idea is to decouple, so again we can change internally without making change to the client, so the client still have the same endpoints. So that's overall the nodes, and everything is wrapped by a container orchestrator. So this is core for the achieving the reactiveness that we want to achieve, because container orchestrator, they can handle the restart, they can handle the health checks of the nodes and all of that. So it's a very reactive architecture, thanks to the container, thanks to the message system that we have at the beginning of the flow. And also the container orchestration we had nodes for observability, so we want to make sure that we are monitoring and we are logging everything about every node. So here is the implementation choice that we decide to move forward. The main architecture is this one, the couple, but we have this implementation as a way to do proof of concepts. So we can see that we are using EMQ as the broker. We are also using Mosquito in some case. As the message broker, we have Kafka, very reliable technology developed by LinkedIn, and also used by many big companies. Backbone of many ETL systems. We have Postgres and Redis as data stores, and also InfluxDB as the time series in this case. And all of the microservices are written in Golang, which is a very lightweight language, a modern, a very new language from 2010, if I recall it right. It also is a language that is cloud first based, so you have many of these cloud services written in Golang. And as the orchestrator, we have Kubernetes, which is the default standard state of the art right now. And for observability, we have Elasticsearch, Kibana, and FluentD at this point. So this is the conceptual view of this architecture. For the next step, we're going to validate this architecture, especially the reactive features of these architectures in a real scenario, which is our lab, our internal research lab. This lab has the proper infrastructure to develop this kind of distributed system research. We have the sensor, we have the actuators, and we have the proper resource and computation and overall infrastructure. You guys can check the information about this lab at this address. And the conclusions from this paper, the beginning of this paper, is that while we have many research around IoT and reactive architectures, we still see a lot of potential for more in-depth exploration of this area, especially using open source and up-to-date, very new technologies we were just showing before. And then the focus here is to enhance the quality of this smart building from hospital to campuses. So the usage of reactive microservices and also cloud patterns will guide and shape the development of the architecture effectively. So we are also using the gateway, we are using bulkhead, we are using circuit break, and all of these are also cloud patterns that we believe is going to improve a lot the scalability and also the reliability, responsiveness of the system. Using open source software, so all the software we are using open source, a lot of potential for customization, low cost of implementation as everything is open source, and that's one of our goals, for optimal results while minimizing the cost of the initial architecture. So this solution contributes to the state of the art in the following ways. We are using a distributed architecture for the IoT context, and we are also following the reactive manifesto. We are also applying cloud patterns and container orchestrators to implement a reactive architecture. And also we are creating a solution that will allows this architecture to be applied to others IoT applications in different sectors. So we have smart campus, industry, smart house, smart hospital, so on. So the idea here is to have a very abstract and base foundation based on the orchestrator, based on the reactive manifesto, so messaging, reliability, responsiveness, and have this in a way that we can adapt to different use cases. For future work, we are focused on implementing these in real-world scenarios, especially in the lab that we have all the infrastructure ready for these tests. And we want to benchmark and illustrate the benefits of this proposed reactive-based solution. Thank you. These are the reference. Thank you for all that are attending the meeting. I hope you guys enjoy this intro to this research. These are some address, so feel free to contact me. And have a great day. Bye bye.